CLion a cross-platform IDE for C and C++. Download now.
Thank you all for getting up nice and early to come out and see my presentation this morning at ACCU in Bristol. My talk, Move Slow and Break Things, is going to be an exploration of how we can try to maintain the effectiveness of C++ as the language evolves without dying under the burden of accumulating technical debt as we add features that the language grows decade after decade. And the move slow part is the notion that, yes, while we want to tame this complexity as we can, while we want to find the ways to improve the code by highlighting certain kinds of errors, we don't want to do so at a rate that makes the product hard to migrate with. So yes, we want to have a velocity where things do get removed from the language over time, but we also want to move at a pace that will maintain our heritage of a strong backwards compatibility story that has been at the heart of a lot of the success of C++. So who am I? I'm Alisdair Meredith. I'm a developer on the BDE team at Bloomberg, working for John Lakos. And I will always say this is a fantastic opportunity if you ever get a chance to work there with John. So that's been a fantastic 15 years I've been there now. And I started as a member of the ISO C++ working group, thanks to Francis here, inviting me to join back in Oxford around about 2003, which, as a pure stroke of luck, was the first meeting for the what would become C++ 11. So I was on the ground floor of that, having completely missed everything that got us to that starting point. And an awful lot of what I'll be talking about is things that we've been trying to do with that original C++ 98. As things move forward, we try to, that's where a lot of the historical baggage might be occurring from. And yes, I'm the person breaking your code. I'm the person who tends to be the garbage collector within the C++ standard committee as features in the move slow side get deprecated. I ultimately tend to be the person who writes the paper to say, and now we're ready to remove that thing from the language, which is the point where it actually starts breaking people's code. So the slow process, we have to remove a feature. At some point, we'll decide that for whatever reason, this particular syntax, this library, is not serving us well. It's masking errors. It's inducing complexity with other new features that have come into the language. So at some point, we'll say we want to do something about this feature, and we'll declare it deprecated. Deprecated is no guarantee of anything. All it says is that we make no guarantees that this feature will be available in future editions of the standard. That is, the ISO terminology of what deprecated means. In terms of how we tend to apply that within WG21, the C++ working group, a feature will be deprecated in the C++ X, some version. The following version, C++ next, we might find out that that deprecation was actually problematic. That feature was being more widely used than we thought. There are good uses of it. So we might consider undeprecating a feature as soon as C++ next, the following edition. If we do wish to proceed through with the idea of removing a feature, though, we will certainly generally go no sooner than C++ later, next edition +1. So two standard editions. So it's a 3-year standard cycle, at least 6 years, where the feature has been deprecated, and hopefully your implementations are giving you deprecation warnings before we even consider removing a feature. Generally, if it's a library feature, we will also not want to remove it unless there's been an alternative facility you can migrate to, so that before the standard comes and takes away the feature, you've already had a chance to migrate to something that the standard supplied that would better solve your problem. A classic example here would be something like standard auto pointer, where there was a desire that you would move from auto pointer to standard unique pointer. So we wouldn't be able to remove auto pointer until you've had at least one edition of the standard working with standard unique pointer. In that case, we took 2 editions. Unique pointer went away in C++ 17. But there was another function we wanted to take away in C++ 17 in the function binders, the not 1, the not 2 functionality, but there was no replacement to move to at that time. So we added the not fun function in C++ 17 that would be the migration strategy, and then we could take away that feature that was done the two standard cycle, but it didn't yet have the alternative to migrate to. That migration was only around for one standard, but the feature can be deprecated long enough that people had already been looking at ways to evolve away. Lambdas help solve the same problem. So as long as we've got that migration for one standard, we tend to be happy. We don't insist on the migration being available for two, but we prefer it, clearly. We also have this feature that came from Stefan Hoyer at Microsoft with the great enabler for being able to remove these library facilities is introduce something that we call zombie names. The standard gives you a specification for how all these different identifiers in the library behave in your program, and we have a bunch of names that are reserved for future usage. Zombie names are reserved for previous standardization, which means that your library vendors, those are still reserved names. They're not available for you to overload and consume, define macros and things to use yourself. But it also means library vendors can continue supplying those features even though the standard has stopped talking about them. And it's therefore between you and your library vendor how quickly they phase out those features that the standard itself no longer wants to spend the time maintaining. And yes, there is a burden and an overhead on maintaining deprecated features as the language evolves, and some of those evolutions impact the library specification. You then have to go and do the maintenance of those features that you deprecated because you didn't want to be doing that. So yes, with this zombie names feature, we get to take the features out of the standard, but that's not yet the end story. It's then your vendors will decide when they're taking them away from you, and they're in control of the pace of whatever the market can tolerate, essentially. So what's my part in this process? I'm the guy who wants to remove everything from Annex D, gated on the at least two standards or one standard to undeprecate. So at the start of every standard cycle, the very first mailing where we process the work, I write a paper that goes through every single feature in Annex D, which is the deprecated features of the standard, and do an analysis to say, is this feature ready yet to be removed, to be undeprecated, or should we just stay in a holding pattern, perhaps because we've not hit those two standard cycle yet? For the next release, I will find the standard where that feature was first introduced. Often that's C++98, but increasingly we're now looking at features that might have been introduced more recently and evolved beyond. I will point out the standard where it was deprecated, because that gives us a gating for how long it is before we can consider removing something. Occasionally we'll find we might have deprecated something just one standard after it was issued, and in that case we might be more eager to remove a feature without waiting the full 6-year cycle. Because if we can remove it before too many vendors have shipped it, and ideally ship that as a defect report, that we put some fix for a feature that had a deprecated tail on it, we can say, no, just do it the right way from the beginning. So knowing how recently something has been removed is also very relevant. And in the middle ground is probably where you're not going to be messing around too much. In general, in the past, I used to file one big paper to try to remove everything all at once. And I then found out that for C++23, nothing got removed because I couldn't remove anything until the whole big paper was processed, and I ran out of time. So none of the moving parts got to move. So for C++26, as we're going to see, I have a new process where I write a specific paper for each individual feature that's going to come out or be proposed to come out, while maintaining the big paper as a just general status update. So if you want to go and follow this work as it's coming along, you find my latest status update paper, and that will have a complete status of all the papers that are being proposed, where they are in the process, working their way through. And at this stage, in terms of C++26, we're not quite finalized yet, but the feature set for C++26 is finalized. And in a meeting in 2 months' time in Bulgaria, we're going to finish the adopting everything. So there's a couple of things we're going to see here. They've not been removed yet, but they're design approved, and the final papers to actually pull the wording should be happening in a couple of months. So after I've just spoken about through here, the basic process I go through about, yes, I will analyze the papers and analyze the features, produce the papers. But removing deprecated features isn't the only way that we might be breaking your code if you migrate to C++26. As we evolve regular language features or add new features, they might have the new syntax might have an interaction with existing code. And if that interaction is going to be too big, too intrusive, we will very carefully consider how we might better design that feature. If the interaction is sufficiently obscure, we might decide that we will proceed ahead, even though that means breaking some code that was never deprecated, because the new feature is worth the cost. Now, obviously, the cost of breaking code and backwards compatibility, we have a fairly high barrier. But probably the most familiar example here would be something like repurposing auto in C++11. The old auto identifier specifier, we would do as much as we could to make sure code that had that wouldn't be broken. But at the end of the day, the auto keyword was redundant in C++98. It was a holdover from the early days of, I think, pre-standard C. So the idea to repurpose that to do type deduction was clearly the way we wanted to go. The amount of code that was using auto with its original semantic to say, I'm declaring a local variable, which meant the same thing without the auto, it just wasn't used that much. So that was a good example of where we might decide that old backwards compatibility was a legacy we were prepared to tolerate breakage on, especially as the fix was so simple. Just don't put the auto there. So then we hit some other common concerns. If we're designing a new language feature, we might need a new keyword. Keywords are very precious real estate in the C++ lexicon, because if you define a keyword, you're taking that identifier permanently away from users. Now, that was reasonable back in the days of C++98, because the amount of C++ code that was out there was much more than it would be today. We're now trying to make amendments to a very mature language that's been out there for 3 decades or more. Almost any identifier we pick is going to be clashing with user code somewhere. And in the worst case, you might be clashing with a macro name. Now, we have our general conventions that we'll use lowercase characters for our identifiers in the standard, and we can hope that our users don't define macros with lowercase letters, because that at least simplifies some of our concerns. Not always the case. Things like attributes. Well, attributes are not in the syntax space where they can clash with user identifiers, but they still have to be concerned about people using them as macros. Library headers. Oddly enough, that's skewing from the hashing include search namespace. So it's very unlikely that users will create headers that don't have a file extension, but technically that's something that, while the new library header, that's a potential breakage. Something we have decided we're no longer worrying about is every library change that you make, every overload that you add, or make something explicit, no except, whatever. No, not no except. No except doesn't come under this constraint, but smart people can write code using, I'm trusting everyone in this room here is familiar with the notion of spin-I. Quick show of hands. Do I need to explain spin-I to anyone? I see one on a certain hand. The idea is when I've got template code, I might have a part of that expression that depends upon some of my template parameters in a way that would be ill-formed when I instantiate that template when I've actually got the concrete type. So I might look up a type name within a class, but then if I instantiate that template with an integer, there's no necessary type name to find. And rather than turning it into a hard error, it just says, okay, that overload drops out of the overload set, I no longer consider it. And therefore, people have, over the years, weaponized this technique to aggressively design their libraries to say, well, if I can create this ability to fall out of the overload set, then I can control and have much more specialized algorithms and look up to find the functions I want. Now, it wasn't created for that reason. There were good reasons that was necessary. But now that that technique is out the bag, we've been playing silly games with that for the last 30 years. And in C++20, we've had concepts and requires clauses that make the spin-I effect so much easier to write and consume when we actually really want that. So the general concern is, anytime we make any change to the library in any interface anywhere, it's observable through code that's trying to do these careful metaprogramming techniques. And in C++26, it's going to get much worse because we have reflection that will allow introspecting on class members and all sorts of things. So the general principle is, If it's observable only through spin-eye or reflection, we're not going to be too concerned about if that breaks code. People who are using those techniques are generally smart enough that they can actually work around whatever problems you've created. And again, as I say, many of the core language editions tend to have surprising corner cases. We work very hard to eliminate those corner cases before we get to publishing the standard, though. And then in the final corner, we've got intentional breakage, where we said, here's a feature that is just wrong. It's unuseful. It's dangerous. If you use it, it's going to cause you more problems than you're going to benefit from. So this, again, very hard for us to say, yes, we actually want to break your code. But if you're in this category, then we probably do want that breakage. Especially, again, if it's a corner case that we can just clean up the language little piece by little piece. The less undefined behavior we have in the language, the more people tend to be comfortable that the language might still be safe to use. So my example here from history in C++11, in C++98, if you had a string literal, you could bind it to a non-const char star. And it was an undefined behavior to ever write through that pointer, but nothing in the language would stop you doing that. C++11, we said, no, we're going to insist that if you're decaying that string literal into a char star, it better be a const char star, otherwise your program would break and fail to compile. We thought that was a good trade-off. Another example we're going to see later on is we might define the behavior where something is undefined. We say, well, if it's undefined behavior, my program's unreliable. But was it undefined for a reason? Or are we at a point where we can say, actually, we have a good behavior there that we can specify in all cases. So let's just do that. And again, remove another ability to hurt yourself from the language. And again, removing undefined behavior is technically not breakage, because if you were relying on it, you didn't have a valid program in the first place. But the fact is that people do tend to rely on these undefined behaviors. So even fixing the issue of the behavior being undefined can lead to some breakage. So with that, we're now going to go through the catalog of things that are changing in C++26. And along the way, I might give you some quick highlights about how the language is changing to highlight why we're making some of these changes. So let's start out. We've got a bunch of new keywords. Any of these keywords that if you're trying to use it as a macro, then that would be a problem. I think it's highly unlikely that most of these would end up being used. But if we take a look, the first set of keywords, we've got contract assert, hopefully not widely used, pre and post. Those identifiers seem to be something that would be widely used. So we did not want to take those as a full keyword. They're what we call a contextual keyword, a keyword that's reserved for use in specific circumstances. So in this case, for the contract testing facility, pre for precondition, post for postcondition, you can put these in a specific place of a function declaration. So they're still perfectly usable as function names in a wide variety of contexts. But now in a place where they weren't previously valid because you weren't allowed an identifier at that point in the function declaration, pre and post now actually have a meaning. Hence, you really better not try and define macros to match them. Next couple of keywords come from the trivial relocation facility that I worked on. And well, the committee never found a keyword that it couldn't make longer. These are not the keywords I chose. Please do not blame me. But the committee wants to be very clear on this, that these keywords, they're an opt-in, but if the opt-in doesn't work, the keyword is ignored, kind of like const expr. So oh, we can make this thing const expr, we'll make it so, but if it's not a pure const expr function, well, unless you try and use it as const expr, you'll never have the worry. In this case, we have a couple of we're trying to say, please make these certain type traits true, but if they can't set it, they remain false. So all the code that gates on it does the correct thing. Hence the if valid suffix that was trying to indicate that, no, I'm not pushing the opt-in, I get it only if the compiler says I could have it. Final new keyword-like thing coming in, we have the indeterminate attribute. This, again, is a neat part of where we're trying to push undefined behavior out of the standard. in previous versions of the standard, if you have an uninitialized local variable and you try to read its value, that's undefined behavior. In C++26, that is now going to be defined but erroneous behavior. By erroneous behavior, we mean, yeah, you've still got a bug in your program, but we're not going to have all the wilds of undefined behavior that can go wrong on you. So you're going to get some value determined by the implementation. It will be a stable value. It's not going to change underneath you, but it's an erroneous value. So when you attempt to use that erroneous value is wrong, which means that the implementation, if it can detect that, might terminate your process. That's a permitted behavior in response to that, but it's not allowed to do all the wild speculative optimizations that says, well, I know that that thing can never be true and therefore I can optimize out all this code. No, it can no longer make those assumptions because the behavior is well defined, but it's still an error that might be flagged up by debuggers, sanitizer tools, and all sorts of third-party tooling can look for these kinds of issues that might not be easy to determine necessarily when the program has been compiled. So the other identifier that we're now taking out of general consumption, in many contexts, I think there's still a couple that might work, is the single underscore, which now becomes the identifier for, this is a scratch variable, I don't care what it's called. And therefore I can have multiple underscores declared in the same scope, or same function scope, but not at class scope. I can't have multiple underscore data members. But this is very handy when I'm just, for instance, I've got a restricted binding. Is a common use case where I might want to have restricted binding. I want to get 2 or 3 of the variables I'm naming and 2 or 3 others I don't care about. I can have multiple underscores in that restricted binding declaration, and I just get the ones I want out. The others are still in the binary, but I have no easy way to use them. I don't have to worry about naming things that I don't want to use. This is basically equivalent to having the maybe unused attribute added to that variable declaration. And because it's now this special identifier, if you were using underscore as a placeholder identifier in your own code, well, if you weren't using it, it'd probably be okay. But there's a chance that now underscores as placeholders in user code might start running into this issue. And again, likewise, it can't be used as a macro name. I know a lot of preprocessor libraries like to use underscore as their own placeholder, so that's a place where things might get caught up. And again, it can't be used as the name of a function like, the name of a parameter for a function like macro. So that's one that maybe on the higher side of things that might turn up, I don't know. Well, we will see. Then as an added bonus, this is one of my papers, I'm trying to attack the nature of undefined behavior in the preprocessor. And one of the things that turned up is that keywords, like hash defined private public, has been a diagnosable error. It wasn't undefined, it wasn't ill-formed no diagnosis required. That has been a diagnosable error since C++98 that none of the implementations actually diagnose. And we know that there's a lot of code out there. People like to use these hacks like define public private public, sorry. But the problem here is the wording that prohibits this was hidden in the library clauses, not in the main core wording part of the standard. So all I'm doing is I'm moving the wording to the right place. We've checked with the compiler vendors and they're all happy to say, okay, we're overdue. We actually ought to start making those checks and saying, no, you're not allowed to define these macros. So I mean, things that you're not allowed to define, any of the keywords, any of the contextual keywords, so final, override, any of the attribute names, other than likely or unlikely, because those were too widely used as macros back in the day, so those particular attributes got an exemption. And the alternative tokens, like and, or, not. But implementations, as long as they diagnose that attempt to abuse the macro name, are allowed to still continue accepting your program, compiling it just as they would before, because all that's required, if that becomes a standard conforming extension, and you can accept an invalid program, as long as you issue a diagnostic saying, oh, I've got an extension, I'm allowing you to do that, then those programs can still compile, and vendors are now happy that they've got a scheme that they can themselves go through the equivalent of a deprecation process where they might go into a strict mode, these are rejected, but they just diagnose them meanwhile. Again, this is not breaking something new. This is just reassuring that the vendors are actually following through on something that we set 30 years ago. Then we have 14 new headers coming in. The yellow ones are the ones that we're hoping to standardize in Sophia. They've not yet been standardized. A quick walk through some of the functionality we're getting. But first things first, fiber context. It looks like fibers have probably missed 26, so I'm not expecting those to actually land in Sophia. That was confirmed for me just in the last week or so, though, so I thought I'd update the slides rather than put it out completely. So what new headers do we get? Language support, we've got contracts and reflection, which are going to bring in, as we saw, keywords and their own features that are going to have some impact. Hopefully those are exciting new features for the language. I think those are two of the big headline features for C++26. We've got a bunch of concurrency stuff. So has the point as an RCU, or for those people who like to get really down close to the metal, SIMD is something that's been wanted for a long time to better exploit those parts of our modern architectures. And concurrent queues, I think, is going to be a really big thing that people have been waiting a long time for. So, yay, concurrent queues is still got one meeting to get in. We're optimistic. Debugging support and general pragmatic support for engineering and helping manage a successful deployment of your code now. So we've got the contract facility, so you can declare your contracts and check them more easily. Debugging is basically we can see whether there's a debugger attached to your process, which can help us with how you might interact with the debugging process. And checked in, which we're getting actually from the C folks, is a bunch of functions that will give you correct behavior with integer overflow, saying I'm trying to add these two numbers together, do it in a well-defined way, because if I write it myself, I'm probably going to write something that has overflows in certain corner cases. It's a much harder problem to write than you naively think. So that's where that header's coming in. And finally, we've got a couple of new data structures, Hive and in-place vector, which I think Alan Talbot's talking about in the other room as we're talking here. And we also got a linear algebra mapping onto the BLAS framework. So moving on to sources of breakage that come from changes to the core language. Again, this is one of my papers trying to remove one of the undefined, something else says it all, removing one undefined behavior at a time. I'm slowly going through the standard and saying, if you've got an undefined behavior, does it serve a good purpose? Or would it be better just to either well-define it or make it ill-formed? And in this case, the issue is I call delete on a pointer to an incomplete type. That is going to be undefined unless you satisfy two very specific conditions. When that type that you deleted is complete somewhere else in the program, it has to be trivial. And that completed type does not have a class-specific delete function. When both of those are satisfied, your program is well-defined. But you can't see that anywhere near the point where you're calling delete. So that's just a big punt into the unknown. And so with no ability to warn with that whole program analysis, this has not been very helpful. To the best of my understanding, the reason that feature works is if I've got a trivial type that doesn't have any of these overloads, I can just ignore it. I'm not going to destroy my object, but operator delete, I can still reclaim the memory. So reclaim the memory, I never run the destructor. It's kind of the behavior that falls out and how your compilers treat deleted any incomplete type. In practice, we said that small, tiny corner case is not worth supporting. The actual use case, if I'm deleting an incomplete type, that's very easily detected by local reasoning. Yes, that type's incomplete, I can make that ill-formed. I wrote the paper saying, let's deprecate it and remove it with the usual 6-year process. And the committee came back to me and said, no, actually, that corner case is so awkward that even the supported case, we don't think is going to be that frequent. Let's just remove that behavior now. So that's going straight out of C++26 without that usual period of deprecation. So what does that look like? Got class X, void destroy. I've got my delete p function. So it will delete my pointer to my incomplete type. I've got a nice empty struct x. So this program is perfectly well defined when I do new x, destroy putter, because it satisfies the rules of there's no funky data members there. As soon as I add a non-trivial destructor or the operator delete overload, this same program, even though everything's in the same translation unit, it's undefined behavior that you couldn't diagnose. So that's the kind of program that we're breaking. I say this now becomes ill-formed. And it's still ill-formed when I go back to the valid program. So I caught the undefined behavior, made that ill-formed. I go back to the previous valid behavior, that is now still ill-formed. So yes, that specific case is where we're breaking programs. And if you were relying on the undefined behavior, your program had undefined behavior before anyway, but yes, we're still going to break it because now you're going to be deterministically broken rather than relying on whatever random behavior your compiler gave you on that particular run. And in this case, this is still well-defined. You'll spot I've turned the destroy function into a class template, a function template. So within the context of the function template, that delete p is deleting a type that's dependent and not yet known at the time I pass the template. But by the time I instantiate the template, X has become complete. So the instantiation of that, the later point in the code down here, is going to be well-defined because at the time of instantiation, the type has become complete. So this pattern is still well-defined. It's just the case where it's not a template that you've got an incomplete type that you're introducing an error. And what was I doing there? Yeah, same thing. I've now got the funky data members. So next feature that's been addressed, comparing arrays. So this is consistency with a change when we introduced the spaceship operator or the three-way comparison operator. We knew that this behavior was not good back then, but because it had been inherited from C and been around for a long, long time, we weren't going to make any changes to it back then, but we deprecated it. For C++26, we're finally going to go through with this removal. So the issue is I've got two arrays, and I compare them, and it doesn't act. You might think I'm comparing the elements of the array. That's a natural assumption. It's not what the old syntax did. So to avoid confusion, we're going to remove it. So I'll just quickly go to my example slide to try to show this. Here we've got three arrays. Is C++23. Some of these things are deprecated. But the idea is if I compare the arrays, A equals A is always going to be true. A equals B. Well, the arrays have the same size, same value, but what's occurring here is a rate of pointer decay. So I'm not comparing the contents of A with the contents of B. I'm comparing the address of A with the address of B. And that's never true. And almost certainly not what I thought I was asking. Right, if A equals C, we'll compile, even though they're arrays of different lengths, because we're just comparing the decayed pointer. I compare A to a null pointer because a rate of pointer decay, that works. And likewise, I compare to the zero literal, same thing. So in C++26, those equality comparisons with another array, they're breaking. Those have been deprecated since C++20, and that will hopefully catch a bunch of errors with code where people are not doing what they thought they were doing. On the other hand, the comparison with null pointers or other pointers was never deprecated, so those will continue to compile, where as long as one of the elements is already a pointer, it will do the rate of pointer decay, it will still do that comparison, because we presume that if you were comparing an array to a pointer, you probably knew what you intended, and the value change of breaking that code and by forcing you to decay the array yourself seemed more problematic in terms of our backwards compatibility story than just maintaining that support. So we break the comparison of arrays, but no more than that. Next one, comparing enumeration with a floating point value. Again, this has been consistency with the spaceship operator. Enumerators, they're always integers, and they're a typed, strong typed integer in theory. So this comparison with floating point was always dubious. And so now if we've just made this ill-formed, If you want to truncate your 256 divided by 3, you can just divide by 3.14, pass to an int at the other side, or promote the int or the enum x with the unary plus operator will promote the type to an int. So that I probably should have had that on that example on the slide a bit better, sorry. So that's how you generally work around that. Just unary plus x, if that's what I actually wanted to do to turn the enumeration into an int. And similarly, comparing enumerations with an enumeration of a different type. So here I'm going with color and light, which both have red, yellow, green, differentiated just by the wee capital letter, which is perfect for making my simple typos to confuse myself in my code. Now, that would happen to compile and work and do the right thing in C++ 23, on the assumption that I'm relying on that mapping, that those enumerators happen to be the same. But there's no guarantee that the two reds have the same value, and the typo would happily let me go through code inspection doing many of the wrong things. So we think this is a useful place. Again, consistency with the spaceship operator, that this kind of accidentally crossing the streams on your enumerations will now be a diagnosable error. And again, if you want to promote either one to an int with a unary plus, that was probably the cheapest in terms of number of characters of maintaining that logic if that is what you wanted. And yes, unary plus might become more of a common thing as it's a workaround for a number of these issues. And similarly, arithmetic with enumeration of a different type. Again, these enumerators, they're typed for a reason. So we're getting better at enforcing our strong type safety. So if I'm trying to do arithmetic, minus, plus, multiplies, any of these operations, and the enumerations are of different type, that will now become a diagnosable error. I'm breaking your code. Then the next set of features that we wanted to tackle were the uses of volatile. Volatile is a very misunderstood and abused part of the C++ language, and generally sows confusion wherever it's used, and often generally doesn't mean what people expect it to mean. So here we've got volatile on a function parameter. What does this volatile do for me? Absolutely nothing, because volatile says something outside the process might be able to change that value. I'm expecting it from an external link to a register or something. These values might change underneath me. That can't happen with a function argument. There's no external mechanism to make that int a change value. So that volatile is serving no purpose. But people will put it there thinking it's doing something. And we're trying to just remove that confusion by saying, it's write what you mean. Meanwhile, we've got the volatile in reference. That's a reference type. That's a reference to a volatile int. That's perfectly fine. It's only when I'm doing the pass by value that the volatile kicks in, or the new volatile rule kicks in to say, that's an error. Similarly, on the return value can't be volatile in practice. So again, this will now become ill-formed in the new version of the language. It's been deprecated since C++ 20. I think it might have been 17, but I think it's 20. Next set of operations where we're tackling the volatile beast. If you look at B equals A, where B and A, one's an int, one's a volatile int, one's a volatile int ref, B equals A is perfectly fine. If we can assign a volatile to a volatile, that's perfectly good. On the other hand, consuming the result of that assignment, well, after the assignment, the thing I'm looking at is volatile. It might have changed again. I have no ability to rely on what that second assignment is going to produce. It's probably not going to give me what I thought A was. So the consuming the result of an assignment is now ill-formed. If you want to do this, you're going to have to do B equals A, then B equals B, or whatever your variables were, as to subsequent expressions or statements. And that way, what's happening in your program will be a lot clearer to whoever has to come along and maintain it next time around. Similarly, the B equals B plus equals 1, the compound assignment, has the same issue. I shouldn't be reading the result of a volatile operation and expecting it to still be the same. Then we get the confusing one. pre-increment or post-increment on a volatile variable will become ill-formed. I say it's been deprecated for at least 2 standards, whereas the compound assignment, the plus equals 1, that's fine. That will still compile and continue to work because that was undeprecated before we ever got to publish a standard that deprecated it. That's because when we tried to deprecate it, we got feedback from the C community, specifically device driver authors, saying that they used the bitwise compound assignments with volatile quite a lot in their code. And they didn't want to lose the ability to have that. That was meaningful in their context. So they specifically asked that we remove the compound assignment of the bitwise operations. And we said, we're not having this strange discontinuity of some but not all. So we just undeprecated all of those. So those compound assignments continue to remain valid. You just can't consume their results. They have to be multiple statements and expressions. As it turned out, C++ didn't follow through with any of the deprecation on the volatile stuff. So we still have a compatibility story there with C now. Another place where volatile kicks in is volatile structured bindings. These just kind of fell out of the syntax as we introduced structured bindings. It wasn't clear that they would ever be useful. So they were deprecated fairly quickly, and now I'm removing them. So what is a volatile structured binding? Well, you can see on volatile int x3, it gives me an array of 3 ints. Where am I using that? Sorry. Okay. So if I do auto, I get 3 volatile ints out. If I do a volatile auto, do I have that on the next slide? Yeah, sorry. The volatile auto, that's a volatile structured binding, that's ill-formed. Likewise, the volatile auto ref, I thought being a reference, that would have been okay. I'm confusing myself with my own slide. But as you see, static assert on, we've got ABC coming from the volatile int. Those autos do deduce the volatile from the array. So your structured binding can still produce volatile qualified types. You just can't declare the binding itself to be volatile qualified. So with that, I'm going to go back and remind myself what I said on the previous slide, because I was looking ahead in my notes to say, So similar thing with a volatile tuple, that because tuple does not have a volatile overload for the get function, I couldn't, this is unrelated to removing the volatile structured bindings. If I've got a volatile tuple, I would expect to be able to decompose it the same way I could the volatile int array. But in practice, because I don't have the get function with a volatile overload that the structured binding API uses, this attempt to use a volatile tuple was always ill-formed and nothing's changed there. So that's reminding myself what that bottom note of the slide was. I probably did those better in the other order. Yeah. So another major piece of work I've been trying to solve is we have undefined behavior in the preprocessor. Now, undefined behavior, sorry, I have a question.
Sorry, I am a little bit slow. Just a couple of slides back. Say removing like volatile from return values. I just had a question. If you assign the return value of a function to a volatile thing, does that disable return value optimization either in practice or in the standard? Or is it just a good thing to think about?
I honestly don't remember, but given it's gone away, I don't think it's going to be a concern. I think it, no, I genuinely don't know. It's one of those dark corners that I'm happy I no longer have to worry about. And again, it might be one of those ones that was implementation dependent rather than guaranteed by the new rules that came in for C++20. Sorry, it's not my corner of the language without, I can figure it out when I sit down with it, but not live on stage. So back to how we're trying to handle undefined behavior in the preprocessor. When you have undefined behavior in your program at runtime, if you have undefined behavior in the function you've written, and that function gets called with bad values, you now have undefined behavior, and bad things can happen on your customer's device. If my program instead is ill-formed, no diagnostic required, we used to think of undefined behavior as a big bad boogie word, but it turns out ill-formed, no diagnostic is stronger. It says any attempt to even run your program if you produce a program, can do bad things on your customer's device regardless of which functionality they call. So it's a much bigger hammer. Then we have undefined behavior at compile time. And some people like to think, well, it's undefined behavior. It's not as bad as ill-formed, no diagnostic required. What this actually says is the undefined behavior is occurring inside your compiler while you are compiling the program. So the act of compiling your program can do any crazy things on your device. So let's really not do that. So we're going through a bunch of places where the standard has undefined behavior as a consequence of saying I can't figure out what I wanted to do with the preprocessor. This is largely a consequence of how we inherited our wording from the C standard for C++ 98. Although C doesn't actually use the terms undefined behavior here, that was the mapping when we turned it into C++. So for example, if defined plus B, well, plus B is not an identifier because plus isn't a valid symbol to start an identifier. So that's undefined behavior that will become ill-formed, diagnostic required, in C++ 26. Now, if defined one is a literal. It can never be a macro name. But rather than being required to diagnose that, up until now, that has just been undefined behavior within your compiler. Similarly, if defined, no argument. Undefined behavior while translating your program. This just makes no sense to me. So we're turning all these into diagnosable errors. Another example, if defined A plus B, doing nothing about this, whether or not it does what you expect. It's defined of the symbol A, which will be 0 or 1, plus whatever B evaluates to, which might be 0 if B is not actually defined as a macro. If I put parentheses around this, A plus B is not a valid identifier, undefined behavior becoming ill-formed. So some of these macro things might be where your programs start to break, where you never had a valid program to begin with, but you didn't realize that. I suspect, again, this might be one of the areas where we get more code breakage than some of the others. So, here we've got a nice big slide. I've got a macro, declare constructor, which takes class, type, and parameter as arguments. I've got my class any, where I'm going to declare a constructor template, where if I have CPP R-value references, I'm working with C++ 11, great, I'll have a tref. On the other hand, if I don't have R-value references yet, I'll just turn it into a copy constructor type thing with the tconstref. This will seem to be a perfectly reasonable way to define this kind of a constructor with a polyfill to work with various dialects of the language. And it's also undefined behavior at compile time, because any use of, what's it called, preprocessor directives, the if defined else end if, within a macro argument list, that's undefined behavior. That will now become ill-formed. I know code like this is written because I have written code like this, and the Microsoft preprocessor will actually turn this into an error for you today, because that's a perfectly valid implementation of undefined behavior when you're compiling. Thank you, Microsoft. So we've already cleaned up all our code that does this because we compile our code on Windows as well as on Linux. So, but yes, that could well be breaking people's code. And the workaround is simple. Why are you trying to do it at one argument at a time? It's much cleaner and clearer anyway if you just surround the feature and just declare each appropriately. So the workaround's not awful. It just might be a bit of burden and maintenance on folks. And again, one of the neat things, because we're just defining undefined behavior, maybe the vendors might choose to backport these kinds of diagnostics all the way back to earlier dialects anyway, because it would be a perfectly good choice back then as well. Another example of something that I don't think people will be writing, but emphasizing that any preprocessor directive in those argument lists. So here the idea is that arguments.h will provide me my arguments for class, type, and param. And then I can close my friend. So yeah, I've got a file that's got 3 identifiers with a comma in them, and that's it. Yes. No, nobody compiles that today, thank goodness. But it was undefined behavior. They could diagnose. It was always their choice. And it turns out, if you put the closing parentheses and semicolon into the file you include rather than here, GCC will compile it, but not with 26. Again, there's notion of bad header names. If any of these header names or attempts to put header names are in your code, they will become from undefined behavior to diagnosable errors. So the first two, you can see we're perhaps hoping for some string concatenation to occur. But string concatenation is phase 6 of the phases of translation of the compiler, whereas the hash include is phase 4 before string concatenation can exist. So these are actually just adjacent tokens, and you're only allowed one token there. So yes, undefined behavior becomes an error. The reason I have two there is I think Microsoft rejects the first one, but accepts the second. It might be the other way around. So Microsoft is quite space sensitive on that today, but both will become ill-formed in 26. Likewise, include without an argument, include without the appropriate open and close, include with just one of the open and close. All undefined today become ill-formed. And similarly, we can try and do these things with macros, same issue, same as we did before, but with ios and stream, I'm trying to fool the compiler into thinking I can put those together and actually get a valid include. And GCC will do that today. But again, that will become, nobody else accepts that, and that will become hopefully generally ill-formed when 26 ships. Undefined behavior in the process. Here we've got the stringization operator, the hash operator, which is a pain to use. So the way you actually get to use it is you have to define macros that are going to use it because it acts on the arguments to the macros, not on macros themselves. So I'm going to have this turn whatever I pass as A to text. So the end result is I'm going to get a string quote delimited surrounding whatever the evaluation of the macro A, the token, turns into. So now I'm going to define backslash as my macro. And when I try to call text backslash, I get undefined behavior that's going to become ill-formed because that expands to slash backslash. Well, that's an escape for the quote character that's inserted there. And now I no longer have a valid string. So yes, that will actually now be diagnosed when that occurs rather than become strange corner case. When dealing with a stringization issue, turned out we're going to have to extend the rules a little bit because it correctly wraps quotes, ticks, and backslashes. It does not correctly, the compiler does not correctly quote or handle escapes for the new line character, which wasn't an issue when this part of the preprocessor was written, but in C++11 we added raw string literals. So now we're going to also, while we're at it, fix this part of the preprocessor so it can correctly stringize things that have raw string literals within them. Next one, the hash operator to stick two things together and make a token. Well, in this case, same thing, you've got to define a macro to do the work because the arguments to the preprocessor operator are arguments to a macro. We're going to define minus to say, yes, I want to have minus word to be what I produced my value auto x. I'm expecting to get a nice integer holding, well, maybe not -0, but a nice 0. But yeah, minus word is taken as a single token, and minus is not a valid start for an identifier. So that should actually be, it's undefined behavior today, it will become ill-formed. How much code that's going to break, I don't know, but hopefully not a large amount. The concern with all these, of course, is you might not write code like this, but how about all those platform libraries that you're depending upon? Again, C is allowed to swallow all these, and without them being well-defined, it's just whatever their platform does. We're saying in C++, a lot of these things now become ill-formed. I'm optimistic there's not going to be too big a fallout for that, but some of these preprocessor ones might be where there's knock-on effects that we're going to find layers deep. Another one that was currently undefined behavior with making ill-formed is attempting to define or undefine any of the predefined macros that are in the standard. So all those CPP underscore feature detection macros, you're not allowed to define or undefine them yourself. The C++ macro itself, or things like the define token that we usually have, the hash define itself. No, you're not allowed to define it to be any of the other, or defined, which is the operator we use for, is this feature defined as an operator? Again, you're not, these are in the list of things you're no longer allowed to use for macro names. And as we said already, we've doubled down on all the regular keywords being an issue here as well. So there's a whole bunch of things that you might have been getting away with as defining unusual macros that might start turning up. But hopefully they're obscure enough that, especially when they've got a double underscore, they're already reserved for the implementation. Hopefully none of these are really going to be ones that catch you out. Then we get the hash line directive. So all of these are invalid uses of hash line. So no argument, an identifier that's not a number, an identifier that's a string that's not preceded by a number, a negative number, a hexadecimal number. No, these things are decimal. I'm not allowed a parenthetical expression to compute the number. It just has to be literally a decimal literal. Hence, hash line 09 is the only valid line on there because that's not interpreted as octal. The one place in the language I found where you can have a leading 0 and it's not going to turn into octal. Likewise, hash line 1023, anything after the 10, it has to be a string literal because that becomes the effective file name. So a line number and the file name. Anything after the file name, again, invalid because I have exactly 1 or 2 arguments there. In addition, we're clamping down a bit on the range of the line. It used to be undefined behavior or unspecified behavior. What would happen if you under or overflowed? Specifically, line 0. There was a question as to whether we should make this well-defined, but the consensus is it's ill-formed, or it's undefined today, therefore we'll keep that in the error set. Likewise, I was concerned about the integer overflow side, the hash line with a number that's just too big. You see, we can go up to int max on a 32-bit integer. But the idea that that overflows, well, what if I do hash line the valid one there, and then there's another line of my code? What happens? So I didn't want to get too far into narrowing this down, but all the compiler vendors said, no, nobody should be dealing with line numbers that high anyway. So 640K, it's all you're ever going to need in line numbers. So yeah, that's actually going to become ill-formed. Last one is something to do with comments. You see, I've got a copy of the standard here for the paragraph directly. It's this obscure corner case where I'm dealing with a / comment, so it's a one-line comment. If there's a form feed or a vertical tab character in that comment, only white space characters can appear between the first form feed or vertical tab and the end of the line. Otherwise, hey, your program's ill-formed, no diagnostic required. It's not undefined behavior. You just don't have a valid program. So our options here are, well, what we've done everywhere else, make the diagnostic required. But that seems like a very arbitrary rule. So the preference is, no, we'll just make that well-defined. Why was this ever anything different? So in this case, we're making something well-defined rather than ill-formed. Next interesting little corner case. This was an optimizer improvement to say, when I have an initializer list, much like when we can coalesce string literals, we should be able to coalesce the data backing an initializer list. So today, if I ran this program, auto A is an initializer list of 5 ints, B is an initializer list of the first 4 items from that list, and C is another initializer list of the trailing 4 elements. These are all distinct initializer lists. So in C++23, these identities, A begin equals B begins, A begin equals C begin, A begin plus 1 equals C begin, they are always false. They're not allowed to overlap. So if you have these kinds of assumptions, you might find a silent change in meaning of your program because we're now allowing these to overlap and be effectively coalesced to have more efficient runtime representations of your program. We're not requiring it. So you can't assume that these will suddenly start turning true instead. It's within the vendor's freedom of implementation that they did not have before. So.
Does that apply also if there's a const qualified? If you had const arrays?
Well, so the question is, do I apply, does the same concern arise with the const qualifier? Well, these are not arrays. These are initializer lists.
Ah, right, okay.
So yes, the const qualifier will have no bearing here. Moving on. We've now got this t dot 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 square bracket n. It's unlikely that you have this in code today, but if you do, we have the example here, it's going to change its meaning. What does this mean now? We now have the ability in C++26 to directly index into a parameter pack. So t dot 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 square bracket n square bracket will now mean I'm referring to the nth element, member, whatever type, whatever it is, of that parameter, template parameter pack. So it could be the type that's there, it could be the value that's there, whatever t happens to correspond to, I'm indexing in and getting one of those. Previously, if we, let's get my slide, yeah. If we look, I have two declarations here, f and g. If we look at f, I'm declaring a function template that takes a pack expansion of types where each argument passed to my function is an array of length 1. And if I look at void g, that says the same thing, and it gives that array argument a name. So the first one just matches overload resolution. The second one, I actually name the feature because I might want to use it in the function definition. So if I now look at trying to call f, well, f without the parameter name is now mapping to this array indexing thing, pack indexing thing. So it says, okay, I will give you the first element of that array, that parameters, and yeah, so I can pass one argument there. It will deduce that's one argument of whatever type it is. So I said, yep, I've got a null putter. I'm not sure that's correct. I can pass null putter to int. I should probably pass 0 there. I'll pull this example straight out of the standard, so I'll probably have to file an issue report against the standard. Doing these issues live. But yes, the idea is that this would, rather than being two arrays, it's one, whatever type is, so it would be the first type, which is an int, and that should no longer be a first type or second type. No, I think there's 0 index, of course, so that should be the double. But in either way, it should, you've now got a single argument there. Whereas with the G function, because I've named the template, the function argument, it doesn't hit that syntax that's doing the pack indexing because they've got the identifier there in the middle. So that continues to mean what the code used to mean. So if you run into this kind of obscure problem, just put an identifier there, even if you're not using it, and the program will continue to mean what it used to mean. Meanwhile, we've got a really fabulous feature in being able to index parameter packs. That was one of the places where I said it was worth the breakage for the feature because the breakage just seems so unlikely in this case. And the feature is very valuable. So that's the end of my running through the core parts of the standard. Now we have changes to the standard library. And big one I'm happy about, we finally got to remove stir stream. If you know about this header was deprecated in C++98. It was never not deprecated. And it's taken us in C++98 to actually remove it. And the reason it's taken so long is what were people going to transition to as a replacement? And nobody wanted to spend any time doing even more work on IO streams to provide something that replaced this functionality. So why were stir stream actually useful in the first place? Stir stream was that basically it was string streams where you took direct control of the memory management of the buffer itself. So we've actually replaced it with two facilities, both of which were provided by Peter Summerlad, who used to be a regular at the ACCU conference, I believe, one of our own. Here, over two standards, add two new features we've got. First of all, the ability to move out of a string stream. So the ability to say I can construct my string in my string stream and then move that ownership of that memory out of that buffer has been supplied. The other issue is I'm not trying to take that memory out. I'm just trying, it's managed externally, but I want to have that view of it. And in that case, we now have span stream that provides the same functionality that says, okay, the buffer is not owned by me. I've got a span viewing the contents of that buffer. So depending upon which of those two features I want, I've got the more specialized tool that does the job for me. And if you want to know more about that, Roger had a fantastic session about this at the 2023 ACCU conference, comparing classic C++ and modern C++. You can find that online on YouTube. Next, we have removing the character conversion facets. These are an obscure feature, again, when you're trying to use I/O streams with the Unicode character types that the I/O streams don't actually support or aren't required to support. But users might have their own streams that are trying to handle this. There are a lot of problems with these types. The error handling when handling corrupt Unicode was non-existent. The features were largely underspecified. And the big concern is locale is all about what locale do I have installed at runtime. These things are supposed to vary depending upon the behavior that's the locale installed at runtime. These facets say, I'm dealing with strict Unicode character types on one side, so there is no change in that locale. And on the other side, whatever I'm getting from the char star or wchar t star, that better also be UTF-8 encoded or UTF-16 encoded, or else I'm corrupting the program. I'm not working with your locale, which is the absolute opposite of what these things are supposed to do. So while we would like to provide a much better replacement for a proper treatment of Unicode in C++, whatever we're doing, these aren't it. So they deprecated them a little while back, those are going. But just as I'm trying to rip those out, somebody noticed that we have similar facets for converting UTF-8 and UTF, or char-8t and char-16t types between each other on the assumption that they're holding correctly valid, well-formed Unicode. And yeah, that's a complete part-time encoding that completely ignores the locale. That's just nonsense in terms of how the facility is designed. The author who added those features agrees it was an error and actually wrote the paper to deprecate them. And talking with the Unicode study group since the last meeting, so this is hot off the press, they were saying, if we get to kill the first step, maybe we should just remove these directly without a period of deprecation. Now that is coming in too late to be addressed in the Sophia meeting where we send out C++26 for its final ballot. It might be in scope for a ballot comment to say, you finished the job you started. So I expect some comments will be filed there, but whether that's deemed out of scope for 26, we don't know yet. Then we've got a couple of convenient functions, wstring convert and wbuffer convert. These had the same kinds of problems as the code conversion facets. They were underspecified. They made assumptions that were hard to establish, and then there was no error handling to detect even if those situations occurred. And rather than spend the huge amount of effort it might take to get these things well specified, the features that are there are very easy for the users to write themselves if they want that kind of interface. With the zombie names clause, the vendors will maintain these as long as they like. But the idea that the standard should spend any more effort on these things, no, we've passed that. So those are now finally coming out for C++26. With a zombie names clause, I don't think you're going to see much breakage in the short term. But as compilers start being more aggressive on the deprecation warnings, we might start seeing some of that code finally going away. Another obscure one, basic string reserve, where I don't pass it an argument. This is basically equivalent to basic string reserve 0. Reserving 0 doesn't sound like it does a lot, and that's because it doesn't. Now, there was a belief at one time that this could be a request to reallocate your buffer with no bytes. So shrink we had a new function, shrink to fit to C++. I think it was in C++11 that was intended to address that concern and be just much more clearly spelled out. It's still a non-binding request, but it's much clearer that that's what you're intending to do. And there's no unusual notion of what this reserve does. So finally, that reserve has been deprecated a few standards now, is coming out. The easy fix is if you're desperate, you can just put the 0 in. That was what it was always doing. You've preserved your old behavior. More likely, you want to change that function call to say shrink to fit instead, because that's probably what you were trying to do. Or you could just remove it because it was doing nothing anyway. Next one, standard allocator has a data member is always equal. This is part of the allocator traits framework, trying to determine whether or not two allocators are equivalent to each other, which is an important part of when we're starting with a lot of the propagation properties of allocators. How does moving allocator container 1 to container 2? Are they compatible or not? Will they can I move elements from one easily into the other? Turns out that when we're trying to create the exception specifications for types, we need to have a compile time determination to say, if I know these things always compare equal, because a large subset of allocators are completely stateless, so they will always compare equal. It'd be nice to have some way to tell the compiler that. So we have this lookup to say, if I had a data member that said is always equal, yes, my type would say I'm always equal. And that obviously applies to standard allocator. So we have that property defined. We have since said, well, we can deduce that property. If my type is empty, then clearly these allocators are always equal unless I do something surprising. Well, set it to false. The problem then is I've now got, in this example, my allocator that derives from standard allocator. My allocator has a data member, it's stateful, and I make my equality comparison operator look at that state. It's no longer guaranteeing that it is always equal. But because I have the inherited data member from std allocator that says these things are always equal, my type is lying. And this is a very easy bug to write. You have to specifically go back here and say, I'm not relying on the detection. I have to add the is always equal property myself. Hence, that was deprecated in C++26 or maybe even 17. And we're finally removing that out in C++26 so that my allocator will now be allowed to deduce because there is no override from the base class, and that will give the right result. So that's a change that will likely be unbreaking. Well, yeah, sorry, that's the change down there. Then we've got the atomic API for shared pointer. This is if you use the atomic types, in addition to the data to the member functions, there's a free function interface that says, atomic load, atomic compare exchange, and all those operations. I then pass my pointer to my atomic variable. That's designed to be the C compatibility interface. And folks were concerned that shared pointers are the kind of things that we might want to have these access to. And because shared pointer has these non-trivial operations, and we couldn't have an atomic shared pointer, so we specifically made this API accessible to shared pointer, so I could pass literally pointers to that shared pointer object, on the condition that the only use of that shared pointer object was through this freestanding function API. So I would have to use the function to load my atomic shared pointer into a non-atomic shared pointer and then work with a non-atomic one. If any of my code anywhere tried, for example, just to dereference that shared pointer that was otherwise controlled by the atomic API, I had no visibility that I've just introduced undefined behavior into my program. This was a very, very subtle way to introduce data races and was highly undesirable. So for C++, I think it was 20, we added atomic shared pointer, where we said, well, it might have non-trivial member functions, but the standard knows about atomic, the standard knows about shared pointer. The standard can make this work, even if users can't do this with their own non-trivial types. So atomic shared pointers safely encapsulates all those atomic accesses and gives you, again, atomic shared pointer is not a shared pointer. I can't dereference it. Or what I can do with my atomic shared pointer is I can say, lock it and give me a shared pointer but it's the same shared data structure, and I can now work with this one non-atomically, and I'm now safe to use that. All the manipulation of the reference cap, that was always had to be atomic thread safe, but multiple accesses to the same shared pointer object, that's where the atomic shared pointer comes in. I hope that's not too confusing. And again, the old free function API had no support for weak pointers at all. We have an atomic weak pointer since C++20. So the time to remove this old, antiquated, dangerous API that was provided for C compatibility, where C has no compatibility with the shared pointer, yeah, its time has come. Again, now we're looking at some of the volatile stuff. Generally, the library has very little support, if any, for volatile qualified types. So we're removing the support from tuple size and tuple element for volatile qualified type parameters. Because it turns out these weren't terribly useful. They were well defined for types like pair and tuple and array, but they didn't provide the get overload. So if I did have a volatile tuple, I still couldn't get the values out of it. So, the thought was that maybe these were important for the structured bindings API, but it turns out they didn't work there either. So these have been deprecated since we deprecated all the other volatile stuff. Those are coming out of C++26. And we have a similar set of operations on variant. That's got its tuple interface, its type breaks interface. Those are also being removed in 26. Again, all the atomic types have volatile qualified overloads for a lot of their operations. And using those spinner rules I mentioned earlier, those operations are enabled only if, on the volatile types, the atomic type itself is lock-free. So if there's locking involved, we're not allowing that to go through with the volatile types. And it turns out we then, in Annex D, with the deprecating stuff, we then undeprecate that, somehow injecting those back into the main standard, going, those specific overloads, yes, they're still there. They're deprecated, and hopefully you'll get a nice diagnostic about that, but it's the same signature, just with that constraint. So we're finally removing those spurious overloads. So whether that's going to start showing up on code, hopefully people aren't doing this with volatile. But yes, again, there is intense window migration strategy here. This is finally diagnosing what was always intended to be a real error. And finally, we've got the atomic initialization API, atomic var init and atomic init. These were part of the original atomic API in C++11 before we understood that, yes, we could just have const expert destructors, and therefore we could safely initialize these things with their const expert default constructor without needing a special macro or other interface to do so. This was also part of the C compatibility interface, but C23 no longer has these. So yeah, those can just come out. And hopefully, since they've been deprecated for quite a while, that's not going to impact any real world code. Okay, I have 10 minutes. Hopefully I've got about 10 slides to go. Hopefully we can go through at this pace. New way that's going to break us, this time at runtime. Contracts and library hardening. So contracts are a new language feature that we can declare preconditions and postconditions on our function declarations. And then the compiler might be able to do something with those and help us find bugs in our code at runtime. Or maybe it's static analysis at compile time. So we've got the ability to use pre and post to put a precondition, postcondition on a function declaration. Contract assert is the equivalent of the assert macro with the new facility. So unlike the assert macro, it's always passed. So if I'm working in a mode where I don't expect those features to be testing my program, I'm still going to make sure my program is valid for when those things get turned on. And again, it's going to be implementation defined when these checks are actually going to be evaluated or not. Because we're falling into the realm of command line switches. Command line switches are completely outside the scope of what the standard itself can specify. So unfortunately, with the contracts facility, there's an awful lot of implementation defined machinery because we expect this all to be there to support compilers providing command line switches for a wide variety of implementation flexibility. So we have these contracts, these annotations with the pre, post, and contract assert. And when a contract is violated, we might call the violation handler, which is just a function we call with the information about the contract itself, the stringization of the code, the source file and line number, where it basically in the source. I've forgotten the name of standard type now for the source info that says, okay, this is where my issue occurred. And there's 4 basic semantics that we can have. And there's an enumeration to tell you which of these that was involved. It's implementation defined how these semantics are established. It could be whole program or command line, say apply this everywhere. Compilers might have their own extensions with attributes or something that says I'll apply this semantic to this specific contract markup. So broadly flexible under the realms of implementation defined, but these are the 4 well-defined behaviors that you might get out of the standard. First of all, ignore. I'm not going to evaluate that contract at all. It's equivalent to end debugging and see that yes, the code's there, it's passed, but it's never going to execute and trigger anything. Then we have the observe semantic, where it says, okay, I'm going to evaluate that predicate. And if it fails, I'm going to call this violation handler with those arguments I was telling you about. And that's a good chance to log and say, I found this issue. But if that function, if the violation handler returns, unlike the terminate handler, yeah, we're going to carry on running the program. So this is a good way of introducing contracts into your code where you've got an established running code base for years. You've probably got some contract violations in there as you start marking the feature and using it that you weren't aware about. So this gives you a chance to find them without crashing your program in testing and continuing to support your existing deployment while you find and clean those up. After a while on observe, you're going to want to promote those contracts to enforce. That's exactly the same as observe, but like terminate, or the terminate handler, if that violation handler returns, we're still going to kill the program and not return control to where we detected the issue. And finally, that brings along quick enforce, which says if the predicate fails, bang, we're just terminating the process. This doesn't even guarantee to give you the information you got from the old assert macro where you get the file and line number. And it's just gone, kill the process. And that turns out to be really important for a bunch of the platform folks who want to harden the standards library, which is where we're going next. They believe that quick enforce is the essential way that they can maintain efficiency of their library implementation while still providing the checks. So it is within the standard, we're introducing a new notion of a hardened precondition that says these preconditions are effectively enforced through something like the contract facility and something like the quick enforce semantic. And we've been very cautious in the first iteration of this just to make sure that there was complete widespread support to say it's non-controversial which of these features we're putting hardened contracts on. So basically, it's those out-of-bounds contracts in containers, spans, and string. So front, back, pop front, pop back. If I've got an empty container, that will now be hardened and terminate my program quickly rather than head off into undefined behavior land. Likewise, out-of-bounds indexing on an operator square bracket. And trying to access the members that were an optional or a standard expected when they're empty. That is not throwing accepted today, that is undefined behavior, and those are now hardened because those are important that those remain efficient operations. As I was saying before, the whole feature with contracts are implementation defined to support power switches. A quick dash at the end. We've got a few features that are now deprecated in C++26. These will be around for another 2 standards, but it's time to start thinking about adapting to them in your code. We've got the Oxford variadic comma, which is the green commas on the screen. Those are optional today. Not having them there is deprecated. You're going to have to start inserting them. So it does remove my favorite idiosyncrasy of having 6 dots in a row. I'll no longer be allowed to do that. There's probably a good reason I'm no longer allowed to do that, but I'll miss it all the same. Memory order consume with the carries dependency attribute was an ambitious feature. We tried to do something with some of the more ambitious hardware memory models, but we never really got this to work in any way other than just being the same as the acquire operations. So we're deprecating those, and they are now synonyms for the acquire operations. So the attribute is gone, not deprecated, sorry. The enumerator in the enum is deprecated, and the kill dependency function that was designed to interact with this is again deprecated and does nothing. Type trait is trivial. Trivial types are basically trivially copyable types with a trivial default constructor. It's not clear that that definition ever served a purpose. It's not used anywhere in the core language of the standard. So we're retiring that term. But the type trait that was defined to report on that term now has a specification that says, yes, if I was what used to be trivial type, I'm still true for that type trait, and it is deprecated. And this is what we did to ispod back around C++17. And because we keep stuffing more of these type traits into that deprecated section, we're holding ispod around until they can all go at the same time. So these might still continue to accumulate for a few more standards yet. And I think that's where I'm running out of time. Thank you.